What if the secret to time travel isn't futuristic technology or wormholes, but already hidden inside the quantum world around us? Forget what you've seen in movies. Recent breakthroughs suggest we might already possess clues to traveling through time, buried within the tiniest particles of reality. Time as we know it from classical physics is simple, steady, and predictable. Newton saw time as absolute and uniform, ticking steadily forward. Einstein changed all of that, proving time isn't absolute but bends under extreme conditions like immense gravity or incredible speeds. Atomic clocks on spacecraft have demonstrated that the faster you move, the slower your time passes. Yet even Einstein's insights might be just the beginning. Enter quantum mechanics, where the rules of reality get blurred. Unlike classical physics, quantum theory deals in probabilities, not certainties. In this strange realm, particles exist in multiple states simultaneously, a phenomenon known as superposition. Imagine a world where multiple realities happen all at once, collapsing into a single event only when observed. Time, too, might behave in similarly bizarre ways. Could the past, present, and future coexist simultaneously, waiting for observation to determine what actually happens? One radical interpretation called the block universe theory suggests just that. Time doesn't actually flow. Instead, past, present, and future exist simultaneously as part of an unchanging, four-dimensional structure. If true, our experience of moving through time might just be a cognitive illusion, a projection of our minds attempting to make sense of a fixed reality. But the strangest quantum phenomenon, entanglement, could hold an even deeper mystery. Entanglement instantly connects two particles, no matter how far apart they are. Change one particle, and its partner reacts instantly, even across vast distances. Could entanglement extend across time too? Imagine altering a particle today and instantly changing its entangled partner in the past or future. Such speculation is controversial, yet recent experiments have left scientists seriously considering these mind-bending possibilities. Then there's quantum tunneling, another reality-defying phenomenon. Particles regularly pass through barriers they shouldn't, something impossible by classical physics standards. Without tunneling, modern electronics wouldn't work, and the sun wouldn't even shine, since fusion relies on this improbable leap. Could tunneling also mean particles, or even information, can bypass not just physical barriers, but temporal ones as well? This leads to a startling possibility. Could the quantum realm itself contain the secret to real-time travel? If we harnessed quantum retrocausality, events from the future influencing the present, or entanglement across different times, our entire understanding of reality could shift. But the potential power to manipulate time raises deep ethical and philosophical dilemmas. Could altering past events cause paradoxes or disrupt reality? Who decides how or if we should ever use such technology? We're standing at the threshold of a quantum era that could redefine human existence. The answers to these questions aren't certain yet, but the scientific community is buzzing with excitement and debate. Quantum physics might be revealing that time travel isn't fantasy, it's physics. Could your future choices literally rewrite your past? Quantum physics says the answer might shock you. Forget time machines and wormholes. Quantum experiments suggest we might already have glimpsed the hidden mechanics of time travel. It starts with the groundbreaking Double Slit experiment, famously showing that observation alone changes particle behavior. But physicist John Wheeler took things further, designing the delayed choice experiment. Incredibly, decisions made after photons pass through barriers appear to retroactively change how those photons behaved in the past. This defies our classical idea of cause and effect, suggesting that the future might influence the past. Building on this is the quantum eraser experiment, another reality-shattering demonstration. Scientists discovered they could erase information about the path a particle took after it passed through barriers, making interference patterns reappear as if past actions were rewritten. This implies that reality itself may hinge on observation and information. Erase the information, and it's like the past never happened. These experiments point directly toward retrocausality, the radical notion that future events can affect past outcomes. Recent quantum research supports this mind-bending possibility, challenging everything we know about time. Could your actions today actually ripple backward, influencing events that already occurred? This brings us to the many worlds interpretation proposed by physicist Hugh Everett. According to this theory, every quantum decision spawns a completely new universe. Reality continuously splits into countless timelines where every possible event unfolds. This intriguing concept neatly sidesteps paradoxes, like the famous grandfather paradox. Instead of altering your original past, any attempt to change history simply shifts you into a new timeline. Recent studies, including experiments involving quantum computers, lend weight to this interpretation. Quantum computers operate by harnessing multiple quantum states simultaneously, potentially allowing them to simulate parallel universes. In 2019, Google's quantum computer, Sycamore, achieved quantum supremacy, performing calculations exponentially faster than classical computers, hinting at the reality of these multiple universes at quantum scales. But what would actual quantum time travel look like in practice? Rather than rewriting history, a time traveler might simply navigate through parallel universes. Every journey backward in time would create or place the traveler in a new, distinct universe, making paradoxes impossible. Yet this introduces the daunting challenge of infinite realities. How would one even navigate such complexity? Einstein himself opened a door to theoretical time travel with closed time-like curves, or CTC says, pathways through space-time looping back to their starting point. Theorized through solutions like Gödel's rotating universe and Tipler cylinders, these loops could enable consistent journeys to the past. However, they require exotic matter possessing negative energy density, something still theoretical and yet to be observed. The concept of negative energy isn't purely theoretical. Scientists have observed phenomena like the Casimir effect, where vacuum fluctuations create measurable negative pressure between plates at microscopic scales. This gives credibility to the possibility of harnessing exotic matter, although scaling this to practical time travel applications remains a massive scientific challenge. Quantum mechanics seems to offer the strongest clues yet that time travel isn't fantasy, but a fundamental possibility. Experiments involving quantum entanglement, tunneling, and retrocausality continually blur the lines between past, present, and future. Right now, scientists are actively exploring how these phenomena could reshape our understanding of reality and time itself. But what happens if quantum time travel becomes reality? The implications would be profound, ethically, philosophically, and scientifically. Humanity would face questions about manipulating reality itself, deciding not just where we go, but when. Quantum mechanics isn't just rewriting textbooks, it's challenging our entire concept of reality itself. Could your future choices literally rewrite your past? Quantum physics says the answer might shock you. Forget time machines and wormholes. Quantum experiments suggest we might already have glimpsed the hidden mechanics of time travel. It starts with the groundbreaking Double Slit experiment, famously showing that observation alone changes particle behavior. But physicist John Wheeler took things further, designing the delayed choice experiment. Incredibly, decisions made after photons pass through barriers appear to retroactively change how those photons behaved in the past. This defies our classical idea of cause and effect, suggesting that the future might influence the past. Building on this is the quantum eraser experiment, another reality-shattering demonstration. Scientists discovered they could erase information about the path a particle took after it passed through barriers, making interference patterns reappear as if past actions were rewritten. This implies that reality itself may hinge on observation and information. Erase the information, and it's like the past never happened. These experiments point directly toward retrocausality, the radical notion that future events can affect past outcomes. Recent quantum research supports this mind-bending possibility, challenging everything we know about time. Could your actions today actually ripple backward, influencing events that already occurred? This brings us to the many worlds interpretation proposed by physicist Hugh Everett. According to this theory, every quantum decision spawns a completely new universe. Reality continuously splits into countless timelines where every possible event unfolds. This intriguing concept neatly sidesteps paradoxes, like the famous grandfather paradox. Instead of altering your original past, any attempt to change history simply shifts you into a new timeline. Recent studies, including experiments involving quantum computers, lend weight to this interpretation. Quantum computers operate by harnessing multiple quantum states simultaneously, potentially allowing them to simulate parallel universes. In 2019, Google's quantum computer, Sycamore, achieved quantum supremacy, performing calculations exponentially faster than classical computers, hinting at the reality of these multiple universes at quantum scales. But what would actual quantum time travel look like in practice? Rather than rewriting history, a time traveler might simply navigate through parallel universes. Every journey backward in time would create or place the traveler in a new, distinct universe, making paradoxes impossible. Yet this introduces the daunting challenge of infinite realities. How would one even navigate such complexity? Einstein himself opened a door to theoretical time travel with closed time-like curves, or CTCS, pathways through spacetime looping back to their starting point. Theorized through solutions like Gödel's rotating universe and Tipler cylinders, these loops could enable consistent journeys to the past. However, they require exotic matter possessing negative energy density, something still theoretical and yet to be observed. The concept of negative energy isn't purely theoretical. Scientists have observed phenomena like the Casimir effect, where vacuum fluctuations create measurable negative pressure between plates at microscopic scales. This gives credibility to the possibility of harnessing exotic matter, although scaling this to practical time travel applications remains a massive scientific challenge. Quantum mechanics seems to offer the strongest clues, yet that time travel isn't fantasy, but a fundamental possibility. Experiments involving quantum entanglement, tunneling, and retrocausality continually blur the lines between past, present, and future. Right now, scientists are actively exploring how these phenomena could reshape our understanding of reality and time itself. But what happens if quantum time travel becomes reality? The implications would be profound, ethically, philosophically, and scientifically. Humanity would face questions about manipulating reality itself, deciding not just where we go, but when. Quantum mechanics isn't just rewriting textbooks, it's challenging our entire concept of reality itself. And the strangest part? We might already have glimpsed the path to real, practical time travel without fully realizing it. Could your future choices literally rewrite your past? Quantum physics says the answer might shock you. Recent quantum experiments suggest we might already have glimpsed hidden mechanisms behind time travel, far surpassing traditional ideas of time machines and wormholes. It starts with the groundbreaking Double Slit experiment, famously demonstrating how observation alone changes particle behavior. Physicist John Wheeler expanded on this, designing the delayed choice experiment. Remarkably, decisions made after photons pass through barriers seem to retroactively influence their past behavior. Physicist David Deutsch further explored these implications, proposing quantum models allowing particles to interact with past versions of themselves in consistent paradox-free timelines. This directly challenges our classical notion of cause and effect, suggesting the future can shape the past. Taking this idea even further, the quantum eraser experiment revealed something extraordinary. Erasing information after the fact can alter particle behavior retroactively. By removing information about a particle's path after it traveled through barriers, scientists found interference patterns reappeared as if history itself had been rewritten. This implies reality isn't fixed, but actively shaped by observation and, crucially, by information itself. Retrocausality builds directly from these startling revelations. Recent quantum research increasingly supports this controversial idea, suggesting events in the future can influence past outcomes. Could the decisions we make today ripple backward, reshaping events that have already occurred? Physicists continue to debate and investigate the implications of these findings, raising profound questions about our understanding of time. The many worlds interpretation proposed by physicist Hugh Everett offers an intriguing solution. According to this theory, every quantum event spawns multiple parallel universes, each unfolding differently. This neatly avoids paradoxes such as the grandfather paradox. Any attempt to alter the past simply creates new timelines. Recent breakthroughs, like Google's quantum supremacy experiment in 2019, support this idea indirectly, indicating quantum computers might indeed access parallel realities at microscopic levels. Closed time-like curves, CTCs, represent another fascinating quantum possibility. Predicted by Einstein's equations, these theoretical loops allow objects or particles to return to their own past. Physicists Kurt Gödel and Frank Tipler developed theoretical models demonstrating how such loops could form, such as Gödel's rotating universe and Tipler's infinitely rotating cylinder. Although physically challenging, experiments using quantum algorithms have successfully simulated CTC-like behavior, lending mathematical credibility to these concepts. One critical element for making CTCs a reality is exotic matter, material with negative energy density. While such matter sounds purely theoretical, it has already been observed experimentally. The Casimir effect measured in laboratories demonstrates that negative energy density naturally occurs due to quantum fluctuations. Although harnessing this phenomenon at a practical scale remains incredibly challenging, it shows quantum mechanics might hold the keys to stabilizing wormholes and creating CTCs. Quantum computing, leveraging principles like entanglement and superposition, is another significant step forward. Quantum computers can simulate complex quantum scenarios that classical computers cannot, including scenarios involving parallel universes and temporal manipulations. As quantum computing advances, these simulations become increasingly sophisticated, allowing scientists unprecedented insight into quantum time travel scenarios. The discovery of time crystals in 2012 by physicist Frank Wilczek opened yet another remarkable avenue. These structures oscillate perpetually without energy input, seemingly defying traditional laws of physics. Time crystals could potentially stabilize localized time loops or manipulate quantum states, creating conditions essential for experimental explorations of temporal phenomena. Quantum mechanics thus continues to hint that practical time travel might not be mere fantasy. Experiments involving quantum entanglement, tunneling, and retrocausality repeatedly blur distinctions between past, present, and future. Scientists worldwide actively research these quantum phenomena, anticipating breakthroughs that could redefine human interaction with time itself. If quantum-based time travel becomes reality, humanity would confront profound ethical, philosophical, and scientific implications. Questions of altering reality, navigating infinite timelines, and managing the paradoxes inherent in temporal manipulation would reshape society entirely. Quantum physics isn't merely rewriting textbooks, it challenges our entire conception of reality. Perhaps the most astonishing revelation is that we may have already uncovered the foundational principles behind quantum time travel, setting the stage for future technologies that today seem unimaginable. What if teleportation and time travel aren't just sci-fi fantasies, but already hidden within quantum physics? Recent discoveries are challenging our understanding of reality, suggesting that quantum mechanics might hold the keys to both instant teleportation and even time travel. Quantum teleportation isn't about physically moving objects, rather, It's the instantaneous transmission of quantum states between particles, no matter the distance. Scientists have successfully teleported photons across large distances, even from Earth to satellites. This incredible achievement hints at deeper possibilities. But what if quantum teleportation doesn't just span space? What if it also bridges time itself? Enter the mind-bending concept of time entanglement. Quantum entanglement, the phenomenon where particles instantly affect each other regardless of distance, may not be limited to spatial connections. Some physicists now propose it could link particles across different points in time. Imagine transmitting information instantly, not just from one location to another, but from the future to the past. Research into quantum memory might soon reveal ways to store and retrieve information across various timelines, changing everything we thought we knew about cause and effect. The ER equals EPR conjecture takes this idea further. Proposed by physicists Juan Maldacena and Leonard Susskind, this groundbreaking theory suggests entangled particles could be connected through microscopic wormholes, tiny Einstein-Rosen bridges. If this theory holds true, wormholes aren't just rare cosmic phenomena. They're fundamental elements of reality itself. Could these microscopic wormholes eventually become practical gateways for teleportation or even for traveling through time? Quantum computing brings these theoretical ideas closer to reality. Unlike classical computers, quantum computers handle complex quantum states effortlessly, making them ideal for simulating time-related phenomena. IBM's quantum experiments have successfully modeled retrocausality, where quantum events appear to influence their own past. Similarly, Google's quantum research demonstrated particles interacting with their past selves in simulated time loops without causing paradoxes. These groundbreaking simulations suggest we might someday practically harness these quantum phenomena. Retrocausality, the astonishing idea that future events can impact the past, is gaining serious scientific consideration. Quantum experiments from IBM and Google have shown how particles can seemingly adjust past behaviors based on future outcomes. Could it be that our future decisions influence events occurring right now? These quantum findings challenge our linear perception of time, suggesting that causality might operate in both directions. Quantum entanglement itself might be the ultimate key to real-time travel. If particles remain consistent across time, could we use entanglement to reliably transmit quantum information backward in time? Upcoming experiments are actively exploring this thrilling possibility, potentially opening doors to previously unimaginable technologies. To fully unlock the potential of quantum time travel, physicists still face their greatest challenge: merging quantum mechanics, which governs microscopic particles, with general relativity, which describes the universe's large-scale structure. Some researchers propose that spacetime itself emerges from quantum entanglement. Achieving this unification might finally grant humanity the tools to manipulate space and time directly. The delayed choice experiment already hints at this incredible possibility, demonstrating that a decision made in the present can retroactively affect past quantum events. This experiment proves that time isn't as fixed or linear as we traditionally assumed. Could mastering this temporal flexibility lead to real controlled time manipulation? Quantum physics is rapidly uncovering shocking realities about teleportation, entanglement, and the very nature of time itself. We might already be on the threshold of quantum-based time travel. What if teleportation and time travel aren't just futuristic fantasies, but secrets already hiding deep within quantum physics? Recent groundbreaking discoveries are radically challenging our traditional ideas about reality, space, and even the nature of time itself, suggesting that quantum mechanics might hold the keys not just to instantaneous teleportation, but potentially to traveling through time. Quantum teleportation isn't the teleportation we've imagined in science fiction. There's no physical transportation of matter. Instead, quantum teleportation instantly transfers quantum states from one particle to another, no matter how far apart they are. Scientists have successfully demonstrated this phenomenon multiple times, teleporting quantum states across significant distances, even between Earth-based laboratories and orbiting satellites. Each successful experiment pushes the boundaries of what's considered possible, proving quantum teleportation is not just theory, but a practical reality today. But could quantum teleportation go even further, beyond just bridging space? This intriguing question brings us to the cutting-edge concept of time entanglement. Quantum entanglement already defies common sense, linking particles instantly across vast distances. But could entanglement also connect particles across different moments in time? Imagine transmitting quantum information backward or forward in time, allowing for direct communication with the past or the future. While still theoretical, scientists are actively exploring these possibilities through advanced quantum memory experiments, potentially revolutionizing our entire understanding of cause, effect, and reality itself. Physicists Juan Maldacena and Leonard Susskind introduced an astonishing theory known as the ER equals EPR conjecture. According to their groundbreaking idea, entangled particles aren't just linked by mysterious quantum connections. They're connected through microscopic wormholes, also known as Einstein-Rosen bridges. If their theory holds true, wormholes wouldn't be rare cosmic anomalies. They'd be a fundamental part of the quantum fabric of reality, constantly forming microscopic pathways through space and possibly even time. Could these microscopic wormholes one day serve as practical portals for instantaneous teleportation, or even facilitate controlled time travel? Quantum computing, a rapidly advancing technology, is already probing these theoretical concepts. Unlike traditional computers that process bits individually, quantum computers leverage quantum states, qubits, that exist simultaneously in multiple conditions, vastly increasing computational power. Recent quantum experiments by IBM and Google have successfully simulated retrocausality, demonstrating particles interacting with their own past states without creating paradoxes. These findings suggest quantum mechanics might inherently allow interactions across time, without contradictions or logical impossibilities. Retrocausality, the startling idea that the future can influence the past, is becoming a seriously considered possibility within quantum physics. Experiments have shown particles seemingly aware of future measurements, altering past behaviors accordingly. Quantum simulations indicate that the future can subtly affect quantum states in the past. This challenges our traditional linear concept of cause and effect, suggesting our decisions today might influence events already thought to be fixed in history. Closed time-like curves, CTCs, offer another fascinating theoretical possibility. Predicted by Einstein's equations, CTCs are loops in spacetime, allowing objects or particles to return to their own past. Physicists like Kurt Gödel and Frank Tipler developed detailed theoretical models, including Gödel's rotating universe and Tipler's infinitely rotating cylinder, both demonstrating how CTCs might form naturally under extreme conditions. Although physically challenging to create, recent quantum algorithmic simulations have shown that particles interacting within these loops could form consistent, paradox-free timelines. Yet achieving practical CTCs faces immense challenges, most notably requiring exotic matter with negative energy density. Surprisingly, negative energy isn't purely theoretical. It has been experimentally observed through phenomena like the Casimir effect. In laboratory experiments, scientists have measured negative energy generated by quantum fluctuations in vacuum conditions. While controlling this exotic matter at larger scales is still beyond current technological capabilities, its very existence offers hope that quantum mechanics could eventually provide practical methods to stabilize wormholes and sustain CTCs. Quantum computing may become the crucial tool for exploring these temporal mysteries practically. By leveraging entanglement and superposition, quantum computers can model complex quantum phenomena far beyond classical computing capabilities. Quantum algorithms have successfully simulated temporal paradoxes, time loops, and retrocausality, providing valuable insights into the quantum foundations of time. As quantum computing rapidly advances, researchers anticipate breakthroughs that could unlock unprecedented control over quantum-based time phenomena. The discovery of time crystals in 2012 by Nobel laureate Frank Wilczek presents yet another exciting avenue. These unique structures perpetually oscillate without needing external energy, apparently defying traditional physical laws. Time crystals could potentially enable experimental control over localized temporal loops, opening new possibilities for manipulating quantum states and exploring temporal anomalies. Future research might harness time crystals for technologies capable of precisely influencing quantum states across time. Quantum physics continues to reveal shocking truths about reality, challenging our deepest-held beliefs about space, causality, and time. Experiments involving quantum entanglement, quantum tunneling, and retrocausality blur traditional boundaries between past, present, and future. Scientists worldwide remain actively engaged in investigating these groundbreaking quantum phenomena, pushing the boundaries of what's considered scientifically possible. If quantum-based time travel ever becomes practical, humanity will face profound ethical, philosophical, and scientific dilemmas. Issues around manipulating past events, navigating infinite timelines, and confronting potential paradoxes will require careful consideration. The very nature of our reality and identity could come into question, fundamentally reshaping society and our understanding of the universe. Quantum physics isn't merely rewriting textbooks, it's challenging the core of human understanding itself. And perhaps the most incredible revelation is this: we might already possess the fundamental knowledge to achieve practical, quantum-based time travel, waiting only for future breakthroughs to unlock this extraordinary potential. The question isn't just whether quantum time travel is possible, but whether we're ready for the reality it will bring. What if the keys to genuine time travel aren't hidden in distant galaxies or futuristic machines, but instead lie deep within the bizarre world of quantum physics and wormholes? Cutting-edge discoveries in quantum mechanics are transforming what we thought was science fiction into plausible reality, challenging our fundamental understanding of space, time, and the nature of the universe itself. Quantum teleportation isn't teleportation as we've imagined in Hollywood movies. There's no instantaneous transfer of physical matter. Instead, quantum teleportation involves transferring quantum states from one particle to another instantly, no matter how far apart they are. Scientists have successfully demonstrated quantum teleportation using photons, instantly sending quantum information over vast distances, even from laboratories on Earth to orbiting satellites. Yet this remarkable achievement raises profound questions. Could quantum teleportation someday extend beyond spatial boundaries to cross through time itself? This intriguing possibility brings us to the fascinating concept known as time entanglement. Quantum entanglement already defies logic by instantly linking particles regardless of physical distance. Could it also connect particles separated by time? Some physicists theorize that quantum entanglement might allow particles in the present to link with states from the past or future, enabling information transmission across different moments in time. If true, this revolutionary idea would radically redefine our understanding of cause, effect, and the nature of reality itself. The ER equals EPR conjecture, introduced by physicists Juan Maldacena and Leonard Susskind, pushes this concept further. According to their groundbreaking theory, entangled particles aren't merely mysteriously connected. They're physically linked through microscopic wormholes, known as Einstein-Rosen bridges. These microscopic wormholes aren't hypothetical anomalies. They might be fundamental, intrinsic features of space-time, constantly forming and existing all around us. Could these microscopic wormholes be harnessed to facilitate instantaneous teleportation or even serve as practical gateways for time travel? Quantum computing adds another compelling dimension to these discussions. Classical computers struggle with simulating quantum phenomena, but quantum computers excel precisely because they exploit quantum mechanics' peculiar rules, such as superposition and entanglement. Recent groundbreaking experiments conducted by tech giants like IBM and Google have successfully simulated phenomena such as retrocausality, where quantum events appear to influence their past states without creating paradoxes. Google's quantum computer Sycamore and IBM's advanced quantum processors have illustrated these scenarios, suggesting that quantum systems inherently avoid contradictions when interacting across time. Retrocausality, the astonishing concept that future events could directly influence past outcomes, is now being seriously considered due to these quantum experiments. Studies have demonstrated that quantum particles behave as if their current states are influenced by future conditions. Could future choices we make genuinely reshape events already perceived as completed? These insights challenge the very essence of our linear perception of time, presenting a future where our choices today might influence what we previously viewed as irreversible past events. Closed time-like curves, CTCs, present yet another fascinating avenue for potential quantum-based time travel. According to Einstein's theory of general relativity, CTCs are loops in space-time allowing objects or particles to return to their own past. Physicists such as Kurt Gödel and Frank Tipler have developed theoretical models like Gödel's rotating universe and Tipler's infinite cylinder, illustrating how such loops might naturally exist. Quantum simulations using advanced algorithms have recently demonstrated that these loops could form without causing paradoxes. However, the creation of stable, practical CTCs remains hindered by the extreme physical conditions required, notably exotic matter possessing negative energy. Surprisingly, negative energy isn't merely theoretical. Scientists have observed the Casimir effect, where negative energy arises naturally through quantum fluctuations in vacuum conditions. While controlling this phenomenon for practical time travel applications remains challenging, its very existence provides essential evidence supporting theoretical time travel frameworks. Quantum mechanics may indeed provide the exotic matter needed to stabilize wormholes and closed time-like curves. Another groundbreaking discovery came in 2012 when physicist Frank Wilczek introduced time crystals, a new state of matter that continuously oscillates without external energy input, defying traditional thermodynamic laws. These perpetual oscillations could potentially stabilize localized quantum time loops, opening doors to controlled laboratory investigations of temporal manipulation. Time crystals represent a fascinating frontier in quantum physics, potentially enabling experimental research into precise time distortions. The implications of quantum mechanics for time travel are profound and far-reaching. As experiments involving quantum teleportation, entanglement, retrocausality, and quantum computing continue to blur the lines between past, present, and future, humanity stands on the brink of revolutionary breakthroughs. Physicists globally remain deeply engaged in exploring these groundbreaking phenomena, hoping to soon unlock practical quantum-based time manipulation. Yet the possibility of quantum-based time travel introduces profound philosophical and ethical challenges. If time becomes manipulable, how would society navigate infinite timelines, avoid paradoxes, and address moral questions surrounding altering history? These issues could fundamentally reshape human society, demanding entirely new frameworks for understanding identity, history, and reality. Quantum physics isn't just rewriting textbooks, it's reshaping our very perception of reality. And perhaps most remarkably, the key to practical time travel may already exist within quantum mechanics, waiting only for future breakthroughs to unlock its extraordinary potential. The real question isn't whether quantum-based time travel is achievable, it's whether humanity is prepared for the profound consequences of harnessing time itself.